Hello students, welcome back to another lovely day of chemistry. Today we are going to start talking about acids and bases, and these are actually things that you've absolutely experienced in your life, but I know a lot of times when we think of acids we think, oh, it's going to dissolve everything, and then you think of bases and maybe you think that they're not as big of a deal, but really they just fall on the same spectrum. And today we're actually going to talk about those, and then you'll get to experience them later on in the lab. So with that, we're actually going to be talking about a few different things. We're going to talk about pH, acids and bases in water, how acids and bases react together, and that's actually usually pretty surprising to students. Their separate properties, and then how do we identify acids and bases? So with this now, one of the easiest ways to talk about pH is it's that scale that I mentioned. So on the left side of this scale, you're going to have acids, and on the right side of the scale, you're going to have bases. And I actually just kind of tell students to remember it like the alphabet. A comes first, B comes second. So you have acids are 1 through, 7, bases are 7 through 14. And what this picture shows is just kind of some of the most basic things that your everyday household items and how they relate to acids and bases. So great example, over here on the left you actually have that hydrochloric acid, which I showed you a bottle of in class and told you I may have spilled on my skin. That is incredibly acidic. I mean, that's down in like the 1 range. You may have even seen a lot of dentist's office will have Coke in here. Coke is incredibly acidic. It actually sits around this 2 to 3 scale on the pH. You have lemons, you have your vinegar, tomatoes are acidic. Bananas are actually acidic. And then you have water is perfectly neutral, and we'll talk about that later. And then you get into, like I mentioned earlier, when I did spill that hydrochloric acid on my skin, best bet was to actually neutralize it with a base, so I added baking soda to it. Then you get into, your soaps, lye, which is used in, making soaps. And anyway, it's based on a power of 10. So as you move from say a pH of 7 to a pH of 6, it's actually 10 times stronger. As you move from a pH of 6 to 5, 10 times stronger, 10 times stronger, and so on. So a pH of 1 compared to like a pH of 7 would be 10 times 10 times 10 times 10 times 10 times 10, essentially like 1,000,000 times stronger. So keep that in mind, and that's because, for those of you that have worked with logs, this is all a logarithmic scale. And really what pH is doing is measuring the amount of hydrogen ions. And keep in mind, a hydrogen ion, realistically, is basically just a single proton. Because that +1 means that whatever electron it had, it actually gave up. So this hydrogen ion that we reference is really just the exact same thing as a single proton, because hydrogen has 1 proton. If it loses that electron, that's it. So an acid is a compound that produces a hydrogen ion, again, basically just a proton, when it's dissolved into water. Some very common ones, HCl, again, that's that bottle that I showed you, which is also known as hydrochloric acid. Then you have HNO3, H2SO4, which is known as sulfuric acid. You don't need to memorize those names or anything. So here we have, and there's actually different types of acids. So here we have strong acids. Are going to totally ionize. I can't remember what word I threw in there. And then you're going to have weak acids are going to partially ionize. And I know it's kind of hard to see in this picture here. Hopefully this whole zooming thing that I'm about to try will actually work. But when you add a strong acid in, such as what you have right here, you can see that it actually completely breaks apart. That proton, again, also known as the H+, is actually completely separated from whatever negative ion it was bonded to. Whereas in a weak acid, you're going to have some of them are going to break apart, but then you're also going to have ones that just kind of stick together. And so that's the difference between strong acid, is they're going to completely break apart, whereas weak acids, they just kind of partially break apart. And bases are going to follow pretty much all of those exact same premises. However, instead of moving to the left to those pHs 1 through 7 like an acid would, a base is just going to move the other way, which is going to have pHs of 7 through 14. So an ionic compound that produces a hydroxide ion, yes, that polyatomic, that OH, when dissolved in water, is known as a base. So some of the common ones: sodium hydroxide, potassium hydroxide, lithium hydroxide. You've absolutely worked with sodium hydroxide and potassium hydroxide pretty often in this class. So a common equation for this: sodium hydroxide, which we start as a solid dissolved in water, is going to break down into sodium plus those hydroxide ions, which again are going to be very, very basic and kind of the definition, I guess, of a base. And then pretty much follows the exact same thing. Strong bases are going to totally ionize, whereas weak bases are going to partially ionize. And so it would look the same thing, except for strong bases are going to completely break apart into these OH ions, whereas some weaker bases are actually going to partially remain together and remain bonded, which means there are less or fewer OHs in the beaker. And so here's actually a very common reaction, and it goes back to when I spilled that HCl on my skin, why did I want to add a base? Well, if you think about it and just think of this as a double replacement reaction, what's going to be produced? Well, what you're going to find is that these are going to switch places, so you're going to end up with NaCl, but what you're actually going to get is H bonded to OH, which hopefully looks familiar to you and you will recognize as water, also known as H2O. So what's really interesting is if you take a strong acid, something with a pH of 1, and I'm not necessarily saying this relates directly to HCl and NaOH, and a strong base, something with like a pH of 14, and you mix them, you literally just get salt water. They basically just meet each other in the middle and come back, and you just produce NaCl and water. So it's really interesting that you can take these two things that would absolutely kill you, and if you were to mix them perfectly and kind of wait, I'm not suggesting you do this by any means, but you would pretty much just create salt water. So acids and bases together, what do they make? Well, they make water, or more specifically, they typically make an ionic compound plus water. So water has a pH of 7, and why does it have a pH of 7? Well, because water just consists of that H+, which indicates acids, bonded to an OH, which is the indicator for a base. And so what do you get when you combine those two together? Well, guess what? You get water, which has a pH of 7 because it's made up of an acid, what indicates acids, and what indicates bases. And then another thing that you're going to have to do is know how to write an equation for a strong acid or weak acid or strong base or weak base. And I want to make sure I give you some examples of that. So strong acid, again, one of the good examples is going to be HCl. And if we start with that as aqueous, what that's going to do is when we talk about a strong acid, we're going to use an arrow, just like we always have, to say that, hey, that's going to break apart into hydrogen ions and chlorine ions. And we don't need to indicate water because, aqueous tells us that it's in water. Weak acid, you're actually going to write a little bit different. A good example of a weak acid would be something like carbonic acid, which, again, you would find in like maybe your Coke or some pops. Carbonic acid is often produced. And that would be H2CO3. And now the big difference, how we indicate strong acid versus weak acid, is we're actually going to use this new type of arrow, which shows that the reaction goes both ways. So H2CO3 is actually going to break into 2H plus aqueous plus this CO3. And I know it seems weird because you look at this and you're like, well, isn't this one producing 2 H pluses versus this is only producing 1? Sure, but what this arrow indicates is that this reaction's actually going both ways. Sometimes these H's, these hydrogen ions are going to interact with these carbonates, and they're going to reproduce this acid. So it's constantly going through this process of recreating, falling apart, recreating, falling apart, whereas this only goes this way. Like that hydrochloric acid is going to stay dissociated. And that's why it's a strong acid. Weak acid, it's going to produce some of these H plus ions, but a lot of it is just going to be staying as this compound, so it's weak. A great example of a strong base that you've worked with would be like potassium hydroxide. Again, we're going to use that single arrow to indicate that this is going to produce potassium ions. And then it's also going to dissociate, that is, almost completely break apart into those hydroxides. Weak base, on the other hand, would actually be, and it looks a little different. Good example of a weak base would be like ammonia. Because what that's going to do is it's actually going to find the water molecules and it's going to go in and rip off one of those H's and it's going to produce NH4, leaving that water molecule to now be an OH minus. But again, this reaction is constantly going through this process of producing this, then going this way, then this way, then this way, then this way, and back and forth. So all I really wanted you to take away is that when we talk about weak acid or weak base, we kind of use this double arrow. When we talk about strong, it goes only one way. And a great way to tell if something is an acid or base, most of the time, if you have something like HCl, well, guess what? That starting with hydrogen probably means it's an acid. However, if something ends in an OH, such as NaOH, it's going to be a base.